Okay, this is a review of energy, which, if you're looking in your textbook, is chapter 11. First problem, we are given the force of gravity of the textbook. We're given the initial height as well as the final height of the desk. We need to find the change in potential energy, which is really just the potential energy final minus potential energy initial. So I mean the change in anything is the final minus initial. So that's how I got that equation. We know the PE is mgh, so we have mgh final minus mgh initial. The only thing that changes is the height.
Teachers, please walk down any student who's been with you for tutoring since 2:30 to the front of the building. Thank you.
And we get 17 joules. Number 2, we have the height. We have the work done. I'm going to go ahead and write out the conservation of energy equation here. The type of energy that we're starting with is work. The type of energy that we're finishing with is potential energy. So those are the two that I'm going to be using here. Now, I know a lot of you can sort of do this in your head, this process of figuring out which variables that you need to use, but writing it out the long way like I did is a sure way to not miss anything. If you write out everything on the left side, everything on the right side, and then you can think about what you actually need. In this case, we don't start with any PE, we don't start with any KE, we just start with the textbook. Then we do work on it, and then what we end up with is PE. So I'm just going to start with work, end with PE, and that's it. I can set up my equations here and then plug in some numbers. What we're solving for is the mass. Here we are given the force that the tennis racket does on the ball. We're given the mass of the ball. We're given the time that the force is acting on the ball. We need to find the KE. So what are we going to do? Well, I want to remind you that force times time is equal to impulse. That's from the last unit, which is change in momentum. The reason I brought this up is because if you look at your variables and you look at your equation for KE, there's really nothing you can do. So you got to see what you're given and what you can possibly do with it. We're given a force and a time. I remember from last unit that's impulse. Okay, so what can I do with impulse? What does impulse mean? I forget. Well, impulse is change in momentum, which is mass times velocity. So if I plug in my numbers here and divide by the mass, I can solve for velocity. So let's go ahead and plug the velocity into KE. And now we're in business. We're given the mass. We're given the force of friction. I should have written newtons after that instead of meters. We're given the final velocity. Okay, so we know our equation for kinetic energy. We just plug that in. I'm going to go ahead and write out the conservation of energy here. Let's see what we're actually dealing with here. The only thing that we're starting with is work. The only thing that we're ending with is KE. So I can set up my equation, work equals KE. I know that work is equal to force times distance. So I can just divide by my distance and find the force. Here I'm given the mass of the train car, I'm given the initial velocity, it's a car. The final velocity is 0 because we're crashing into a tree. We've got to find the KE, or rather the change in KE, so that the change in KE would be KE final minus KE initial. KE final is really going to go to 0 because that VF is 0. But my KE initial will be a positive number here. Of course, it's going to come out negative because we're subtracting it, and that makes sense. We're losing energy when you crash into a tree, so it's going to be a negative value there. Here it says, what is the work done? Well, what is work? Work is equal to change in energy. It doesn't matter what kind of energy. In this problem, work is equal to change in kinetic energy. But work is equal to any kind of change in energy. It could be PE, it could be KE, it could be spring energy, it could be Einstein's energy of mass, E equals mc squared. It doesn't matter. Work is just equal to change in energy. So I've already figured out that my change in kinetic energy is negative 144,000 joules. So then that's also the work, because work is just change in energy. It doesn't matter what kind of energy it is. Alright, and now if we're given the distance, how do we find the force? Well, I know that work is equal to Fd, so I can sub in my Fd instead of the W, and then just divide and solve for force. We are given the force applied to the stone here. We are given the distance that it's applied. We're given the force of gravity of the stone. I'm going to go ahead and write out my conservation of energy here. Think about what you're starting with and what are you ending with. We're not starting with anything except work, and then what we're ending up with is PE. Let me pause there to explain this real quick. We're not starting with any PE because we're not starting at any initial height. We're not starting with KE because we're not starting with any initial movement. But we are starting with work because we're applying a force. Anytime you see the word force, you know that you have some sort of work. What you're ending with is PE. Well, why am I not ending with KE? I thought I was throwing a rock into the air. Well, yeah, of course, as the rock is flying through the air, it has KE. But the question is asking at the very, very top of the rock's trajectory, how high does it go? And remember, at the very top of any object's trajectory, it stops for a second and then goes back down. So when it stops for that split second, it has no KE, it only has PE. Alright, so we plug in our equations for work and for PE, and we can go ahead and solve for the height. We're given the force of gravity of the sack of grain. We're given the height. We got to find the work. We can just plug in our force and distance here. Remember, work is equal to change in energy. I don't care what kind of energy it is. It doesn't matter if it's PE, KE, whatever. In this case, it happens to be PE. So work is equal to change in potential energy. So it's going to be the same thing. I'm going to write out a little mini version of our conservation of energy here. I left work out because we don't need it in this case. So this is a conservation of energy for when you drop the grain. I'm on section 3 now here, question 7, part 3. When you drop it, you're starting with PE, right? Because it's at the top of the grain elevator. And then when it's just before it hits the bottom, the only thing you have is KE. So what we're starting with is PE because it's at the very top. What you're ending with is KE because it's about to hit the ground. So now I just need to plug in my my formula for PE and KE here. Actually, I already know my PE, and I can just plug in for KE, and there we go. So you can see here it's the same value for all the answers, the same magnitude, and that is because it's the same energy. I mean, if you put in 4,900 joules of work, then that's how much PE you've gained, and then if you drop it, that's how much KE you've gained. We have the mass of a railroad car. We have the final velocity after the collision. We have the initial velocity before the collision. This is a throwback. You've got to remember what momentum is, mass times velocity, so we can just plug in our mass here and our velocity. So part B here, this is an error, I'm sorry. Momentum should be conserved. You should have the same momentum before and afterwards, but if you actually plug in the numbers, then they're not the same. So I apologize. Should be the same. Before the collision, you can do 1/2 mv squared, just using the mass of the one railroad car and the velocity of the one railroad car. And then after the collision, the same thing. Your formula for KE is 1/2 mv squared, but this time your mass is going to be double what it was, so I put a little 2 there. And then your velocity is going to be different too. So you can just plug those in yourself and see what you get. We have a cart that's about to roll down a hill. We're given the mass and the height and the force of friction. This is a before and after scenario, so we got to start with our law of conservation of energy up here, and think about what you start with and what you end with. You have a ramp at the top of a hill, so that's PE, and then when it rolls down to the bottom, that's KE. So we just plug in our equations for PE and KE. I want to solve for velocity right now, so I'm going to leave that as a variable and solve for the velocity. Masses cancel out to save time. Alright, so I got my velocity here. I want to remind you that F equals ma, Newton's second law, so I can find the acceleration due to friction. Let's stop there and take a breath. So I used the conservation of energy to find the velocity at the bottom of the ramp, and then I used Newton's second law here to divide by the mass and find the acceleration due to friction. So now I have a velocity and I have an acceleration. So we can think back to our kinematics equations and think about which one will allow us to solve for the distance. It turns out this one right here is the one to use. I'm going to rearrange it solving for d. There's my velocity that I found, and then there's my acceleration that I found there at the bottom. And then your answer will be 1.3 meters. We're given the height, we're given the mass. Go ahead and write out the conservation of energy here. Think about what you're starting with before he jumps. Think about what you have after he jumps. We don't have any KE or PE before he jumps. He's just standing on the ground. I know, of course in real life he's running up, he's moving. We've all seen a high jump before, but this is high school physics. You got to think about what happens right before and right after. Right before, he doesn't have any sort of energy. He's about to do work. He's bending his legs and he's going to jump. That is your work. And then afterwards, he has potential energy when he's at the top of his height. So those are the two things that we're dealing with in this problem. So let's plug in our formula here for PE. And we can find the work required by the high jumper. Here we have Ryan jumping into a foam pit here. Let's think about exactly what's going on. He's jumping off the building, and so he's got PE when he starts, right? Because he's at the top. And then when he's at the bottom, he's got no energy. How do I know he has no energy? Well, think about it. When he falls into the pit of foam and he comes to a complete stop. He's just stopped there in the pit. He's got no PE. He's got no KE. He's just sitting there. And then before he jumps, he's got PE. Alright, so that's my before and after. So his PE, let's go ahead and just write out the whole conservation of momentum here. What we're starting with is PE. What we're ending with, and we have work, the work done by the ball pit to stop him, and then what we end up with is nothing. So we can rearrange. We know that mgh is going to equal work. So we can see that height and distance here are related with a linear relationship. So again, we are starting with PE. We're ending with nothing. Well, you can't just lose energy. You can't just start with a bunch of PE and have it disappear. Where does all that energy go? Well, it's taken away by work, the work of the ball pit. When Ryan hits the ball pit, the foam is doing work on him to stop it, and that work must be equal to whatever PE he started with. You can't just have energy disappear. Whatever energy he started with had to have been taken away by work. That's why mgh equals work. It's really negative because it's stopping him. So let's think about how the height of his PE is related to the distance of the work. We can see that they are directly related. So if one increases by 5, then the other one's going to increase by 5. So for this particular problem, the answer would be 5 meters, because if his height is 5 times greater than it was originally, then the distance of the ball pit needs to be 5 times greater than it was initially. We have the mass of a linebacker given, we have the mass of a defensive end given, and they come to a complete stop. Let's think about this. Conservation of momentum. Momentum initial equals momentum final. We know that the momentum final is 0 because he comes to a stop. So whatever their momentum is going both ways, they need to add up to 0. So if they both add up to 0, what does that mean? Well, it means that they're both equal. They have the same change in momentum. Alright? So that would be the answer to part 1. They have the same change in momentum. Part 2, which player had the greater kinetic energy? Well, let's think about this. Let's plug in the masses on the diagram. I have 110 kilograms for that guy, 150 for that guy. Let's make up some velocities. I'm going to make up 1 for that guy, and let's see what it would be for the other guy. We know momentum is conserved, so I can set mv equal to mv over here. And for my velocity for the other guy, I get 1.36. So all I did here, I arbitrarily just chose a velocity for 1. I just made it 1 meter per second. And then I plug into my conservation of momentum equation, and I get the arbitrary velocity of the other one. Turns out it's 1.36. So now that I have these numbers, I can plug it into my KE equation and see which one would be bigger, and then I'll have the answer to my question. So for the linebacker, I'm doing 1/2 mv squared right here with my real mass and my arbitrary velocity, and I'm going to do 1/2 mv squared again for the defensive end using the given mass and my arbitrary velocity of 1. If you plug it in, you'll see that the KE for the linebacker is greater. We're given the mass. We're also given the initial height. We're given the mass of the antelope. So the m sub w is mass of Miss Watson, and m sub a is the mass of the antelope. And then the height final is what we're solving for. Well, let's look at our conservation of energy here. What are we starting with? What are we ending with? This one's kind of fun. I like this. We're starting with PE, and we're also ending with PE. You're starting on a tree branch, just standing there, and then you jump and you scoop down, you grab the baby lion, and then you end up on another tree branch. So the only thing we're dealing with here is the initial PE and the final PE. Well, what about all that movement? I thought we were swinging through the trees. Yeah, we're swinging through the trees. While you're swinging, sure you have KE. You have plenty of KE while you're swinging. But we're just talking about the tree branch that she jumps from and the tree branch that she lands on. So we're only concerning ourselves with PE when it comes to before and after scenarios. So let's check out our formula for PE here, MGH and MGH. Let's plug in the mass for just Miss Watson before, and then the mass of Miss Watson and the antelope afterwards. The only variable I have here is my height at the end. The gravities cancel out if you want to save time. I'm going to solve for h here, and you get 8.68 meters. I hope this helped.